In this video, I'm going to solve some more FLeA questions. So I'm going to start with the 2006 question. I don't know what number it is off the top of my head. It's multiple choice. It asks, which area represents the area for resilience? Well, the answer is A. It's the green area, the area that is under the curve up to the proportional limit, or the elastic limit technically, I guess. If we have A plus B, we call that toughness. The purple area is the plastic range, so that gives you an idea of how plastic something is. But yeah, green area is resilience, green plus purple, or A plus B is toughness. Okay, moving on. Resilience is how much energy something can absorb before and still return to its original shape. I occasionally talk about when I failed an assessment. I was told by my lecturer to be more resilient. That did not improve my opinion of that lecturer. Okay, so then we have a 2007 question. I've already just taken all the important parts of the question out. So it's pretty standard E equals FLeA, except we need to rewrite. So we know that E equals FL over little ea, but we can then rewrite that. We can substitute the e's can swap. So in this case, E is going to equal, remember to make sure that we're always working in newtons. Our length has to be in millimeters. Now, this here, I didn't change our E. Our Young's modulus has to be written in megapascals for the thing to work. So, there we go, good catch. Megapascals. So, 210 times 1,000 times the area has been given. Always check that it's the area that's been given. Often they'll give us the diameter, so that makes for a very different answer. So those zeros cancel out, and I will type this in. Okay, 1100 times 10, I could just add an extra 0, divided by brackets, 210 times 37 equals, I get 1.4, yeah, 1, something like that, equals 1.4. The answer I think wants to be a little bit higher, but I'm happy with that, millimeters. So that's 2007. Okay, the next question is from the 2018 paper. The 2018 paper asks which one represents, is a stress strain curve that represents, so stress strain, and it says which one represents glass under tension. Well, glass is not very ductile, so it's going to be that one, because it's the only one that doesn't really have much ductility. Okay, still on question 2010, we then have, we're asked to find what I call punching shear, or ribbon shear is probably the better term for it. Punching shear is a very specific term. I call this ribbon shear, so I like to think of this area. The area that's being cut is this area here. Now, the link is that there is what's being cut. That area is what's being cut. And I like to think of that being like a ribbon. It's also similar to a cookie cutter. The idea is that we're not squashing the whole thing. What we're doing is we're cutting the edge, and so the area that is being used in this question is there. Now this isn't strictly FLeA because we're only interested in stress, but stress equals force over area. In this case, we're given the stress, so what we need to do is we need to rewrite that, and we can swap those two around so that we say that, what are we finding? We must be looking for, oh, okay. Hold on, I'm going to get the question up. Okay, we're looking for the force. Okay, that makes sense. I just want to check. So F equals area times shear, or shear stress, which is same as regular stress. So what we can do is we need to find the area. The area is what's important here. So the area is going to equal to the circumference times the height. So the circumference is equal to diameter times pi, and then times the height or the thickness. So in this case, area is going to equal to the diameter is 10 pi times 3. 30 pi is going to be equal to like 90 something. 30 pi equals 94.2 millimeters. So that means that if we substitute this value here, we have 94.2 multiplied by 450. Because we're using millimeters and megapascals, that should work, but our answer is always going to be in base units of newtons. Okay, so 94 times 450 equals 42,400 newtons, which we could write, the answer is C, which they've written as 42.4 kilonewtons. So the answer is C. Okay, so I can now clear this part of the board. Done here. Before I go to this one on the bottom, which is similar but different, we're going to go back to the 2012 question, which I don't have that one ready. So feel free to click forward. I won't know. Okay, so that's right. To save myself time, printed it. Okay, so for the first question, we're told that there's three 30 millimeter diameter cables that support an elevator car. Now, it says that the yield stress, okay, so I'm going to write that down. So there's three. Now, I have read this question more than once, and I have not read 3. I've just seen it as the. So it's really important to get that. So there's 3 times 30 millimeter diameter cables. The yield stress, right, so that's the allowable stress that we can work up to, is 200 megapascals. And then the safe working load is, so the F that we're allowed is 224 times gravity. Okay. So it says, find the factor of safety. So what we can do is we can find, so this is the allowable, I'll write yield because that's the information they've given us. And what we're going to say here is we're going to say the area, we have to do the area first. So area equals 3 times pi d squared on 4. So we've got 30 squared times pi divided by 4 times 3, because there's 3 cables, equals 2121 millimeters squared, and that's for the area of 3 cables. And so our actual, right, that's our maximum load. So this is F max. The maximum shear is going to be equal to 21991 divided by 2121 equals, so let's have a look at that. 21991 divided by answer equals 10.4 megapascals. We go together like megapascals and millimeters squared. Now, what we want to work out is the factor of safety. Factor of safety is equal to the maximum, the allowable divided by the maximum. So what we've got here is the yield divided by the max. So what we've got here is 200, 1004 divided by 200. And, I've got a factor of safety less than 1, means I've written my numbers the wrong way. I think I wrote the formula right here, but I've written the number wrong. Okay, that's what I did. I used the wrong symbol. I divided by 200. So, yes, yield is 200 divided by 10.4. There we go. Okay, so I used estimation to figure out that I'd done something wrong. it's unlikely that we're going to have a factor of safety less than 1. So I get an answer of 19. Now I'm pretty sure the HSC, because I have the answers literally in front of me, they multiplied by 10 instead of by 9.8 for gravity, but they got an answer that's pretty close. They got 18.8, I've got 19.2. That is a huge factor of safety, but it should be worth noting that elevators are the safest form of transport. There are very few fatalities. The fatalities that do happen in elevators are almost always service technicians who are operating who are not during regular operation. Okay, so the last question we're going to look at is this one here. This is from a trial. This is from the trial we did in 2013. And it says that, okay, I think it's a very hard question, but it's worth going through. I think it's a good question, it's a very hard one. So it says, what is the stress acting, I'm going to read the question out. A 50 kilonewton load, which I have not shown, but the question does, they draw an arrow and they say 50 kilonewton load, is applied to a 35 millimeter wide and 10 millimeter thick steel plate as shown. A 10 millimeter hole diameter is drilled through the plate. What is the maximum stress in the plate when the load is acting? Okay, so the thing is here, this is under tension, and tension, we talk about that expression, chain is only as strong as its weakest link, that if we were to cut through this section here, if we were to cut through that section there, through the middle of the beam, what we'd see is 35 minus 10, it's going to give us 25, so it's going to give us 12 and a half on each side. Maybe that would be. I'm being a stickler for dimensions at the moment. It's probably better. Okay, that's what we would see. We'd see this hole drilled through the beam, or the plate rather, and we'd see that area being cut through. Now, in tension, we have to worry about the smallest area. The chain is only as strong as its weakest link. This plate is only as strong as its weakest location, right? And this is the area where it's going to have the least area. We'll look at what that area is in a second, but I just want to quickly say, and I wouldn't really write this, but I'd say, certainly in actual practice, if this is in compression and there's a bolt in here, we don't worry about it. And the reason for that is because the bolt is presumably just as strong as the material that it's going into, if not stronger. So we don't reduce bolt holes for compression, we only reduce bolt holes for tension. If this is 35, and this area in the middle is 10, that means these two areas here add up to 25. So this is 12 and a half and 12 and a half. But effectively, we could squash those two areas down, and so the area is effectively equal to 25 by 12, or by 10. So as far as the tension area is concerned, the tension area is effectively 25 by 10. So that's what we're going to write. Okay, so we're finding the stress. The stress equals force over area. And area in this case is equal, so I'm going to write area T for tension, because it'd be different if it was compression, is going to be equal to 250 millimeters squared. And then the force is 500, so 50, so I can just write 50 divided by 250 force over area, and that's going to give me, just checking, we're in kilonewtons. Okay. Always check that you're in newtons, but I could also say that I was going to get a stress that was less than 1. My quick maths told me that something was going on that was going to be terribly, terribly wrong here. So when we take 50, 1, 2, 3,000 divided by 250, we get an answer of 200 megapascals. We go together like megapascals and millimeters squared. So we're using millimeters, so we're going to get our answer in megapascals. And that is correct. That is 200. It's also a reasonable answer. The next question is just finding the shear force required to punch a 10 mil hole. So again, we're talking about the ribbon area. I will clear this area now. So the ribbon area, I'm going to make the ribbon area blue, is going to be equal to this height, so this circumference, multiplied by the thickness of the plate. It's going to be equal to that. So I could draw that up here. Area is equal to pi, diameter times pi times height. Okay, we can calculate that. I'll calculate it here. Diameter is 10, pi, height is 10, so it's going to be equal to 100 pi. Area is going to equal 314 millimeters squared, because I know pi to that level of accuracy. What is our force? The shear strength of the plate in question 14 is 220, so they've given us that. They've told us what they want to do is they want to find the force. Okay, so they've told us stress equals force over area, we know that. So if we want to find force, therefore force equals area times stress. The stress that's given is, I'm just going to write in this given. So F equals 314 multiplied by 2 to 2.8. I'm going to put that into the calculator and we'll see what we get. 100 pi times 2 to 2.8 equals, I get 69.999, which we're going to round up to 70, which is A. I'll write the answer though. Equals 69.994, and that's in newtons. So the answer is going to be 70 kilonewtons, which is A. Excellent. They are our FLeA questions.